We even made close it up. And then the question is, how can we compute such things? And since it is so simple, I want to tell you how to do it. If we have such a straight strip, we can take here this middle line. This straight line which lies precisely in the middle. And then if we fold this up in space, deform it, isometrically deform it, we get such a paper strip in space, 3D. We again have this middle curve now. It's not straight anymore, it is a curve. And the question is, how do we get such a strip starting from this curve? And the thing is the following. And here I'm not sure whether you know about the osculating plane of a curve, and the mathematicians must know, and maybe the others don't know. So let us take again a polyline. And then we refine, we make it finer, and in the limit we get a smooth curve. Right? This is refinement. In the limit we get a smooth curve. If we take two neighboring points here, we have an edge of this polyline. Here we have an edge of the polyline, and in the limit, of course, we have a tangent. We know this. We've just had it before. If we take two neighboring edges, we have here this plane, which is actually a plane on this model which I had before, on this developable surface model. And here we have a plane. Here this wedge will be a little smaller, but the plane itself is bigger. Yeah, it's a big, nice plane. So what is the limit of this plane? It is a limit of this plane. Yeah, is the plane which connects three neighboring points on the polyline. This, and this. In this plane. Yeah? All three lie in this plane. And in the limit, we must get a certain plane. This is called the osculating plane of this curve. In relation to what I have said before, a curve has a surface formed by its tangents, and this is a developable surface. And the plane which I'm talking about now is this constant tangent plane along the developable surface. So this constant tangent plane, the limit of the connection plane of three consecutive points, is the osculating plane. So the osculating plane is spanned here in the discrete model by three consecutive vertices. And here, if we have a curve C parameterized with respect to a parameter t, so first, second, and third coordinate function depending on t, then we can take the first derivative c dot. This should be the first derivative with respect to t. And you know that this is a tangent vector. C dot is in direction of the tangent. And you can then take the second derivative, c double dot. And this will turn out to be a vector which lies in this plane. So let's say here is this vector c double dot, and it lies in this plane. So the osculating plane is this plane which is spanned by the first two derivative vectors, by the first and the second derivative vector in the parametrization of a curve. So we have, for a curve, at a point we do have the tangent. And then we have this natural plane, the osculating plane. In the osculating plane, no, I do not need this. What I need a plane now which is orthogonal to the osculating plane. So, curve, tangent. Here's the tangent vector c dot. First derivative, say somewhere here, the second derivative, c double dot, this spans this plane, and we take a plane which is orthogonal to this osculating plane. Is this clear? It's called the rectifying plane. And now, if along this curve M, along this curve M, at each point we have such a rectifying plane. So here this C and C dot compose the osculating plane. And orthogonal to it under a right angle, but through the tangent, is the rectifying plane. Along a curve, the rectifying plane will change smoothly, and we can compute the envelope. The envelope must be a developable surface, and if you develop this developable surface into the plane, this curve M will appear as a straight line. This is why it is called rectifying. It makes your curve straight. So you can ask the question, I give you a space curve. How do you have to pass a developable surface through this curve so that after developing in the plane, this curve becomes straight? And the answer is, take the envelope of rectifying planes along the curve, and then in the development, the thing will be straight. So the question is, why is it straight? Yeah? And it is straight because the following thing happens. If you have a curve, maybe I do it first the following. If I take an arbitrary parametrization of my curve, so I hope it's clear that a curve has many representations depending on a parameter t. Think of a circle in the plane. It can be written as radius times cosine t and radius times sine t, but you could also do a different thing with some square root. You prescribe x equals t and then y equals some expression with a square root, so it's quite obvious. So there's many parametrizations. And there is one parametrization which is called the arc length parametrization. If for theory, it's very good parametrization. This means that you traverse your curve with constant speed 1. This is an arc length parametrization. For an arc length parametrization, it turns out, arc length, the differential geometers write a prime. Derivative with respect to arc length is c prime. This has length 1 senses. The arc length, by the way, of a curve c of t, the arc length is integral norm c dot of t dt. So this is the arc is not a nice function. So even for a circle, of course, arc length parametrization is easy, but for an ellipse, it's already complicated. But in theory, it exists, and then arc length parametrization, I draw it onto this side. C double dot would be orthogonal to C dot. This is clear because for an arc length parametrization, this C prime has norm 1. Right? So you can say the vector C prime squared multiplied by itself in scalar multiplication equals 1. And by differentiation, you get 2 times C prime, 2 times C prime times C double prime equals 0. This we can cancel away. So C dot, C prime and C double prime form a right angle. And this is called, this C double prime is called the curvature vector of the curve. And now, if we have a surface and a curve on this surface, we can parameterize, in theory, our curve with respect to arc length, C of S. We have a curvature vector, C double prime, and this curvature vector has a tangential component and a normal component. So here we have the surface normal, and since here was somewhere the tangent plane, now this I do away, and it has, say, some component tangential and some component normal, right? There's a vector, it has a tangential and a normal component. The length of the normal component, also I did not tell you yesterday, is exactly this normal curvature which we talked about. And the length of the tangential component, tangential to the surface, yeah, is the geodesic curvature. So, now, if our vector c double prime is the normal vector, it has only a normal component, and the geodesic component is 0. This geodesic curvature here of the curve has an interesting property, namely, if I have a developable surface and I take a curve, then the geodesic curvature will be preserved when I develop into the plane. This is why it is called geodesic curvature. This is something that lives in the surface, and if I map isometrically into the plane, it is preserved. This means if a curve on our surface has a vanishing geodesic curvature after the development, I must have a curve in the plane which has vanishing curvature everywhere. It can only be a straight line. So the way to get a straight line in the development is to look for a curve which has vanishing geodesic curvature. What I have said here implies I can only get this vanishing geodesic curvature if my osculating plane of this curve is orthogonal to the tangent plane of my developable surface. And this is why I say if you are giving this middle curve, you look at the osculating plane, you take a plane orthogonal to it as a tangent plane of your developable surface, because then you have ensured that the geodesic curvature is 0. So this geodesic curvature is important, and it will pop up. Oh, I get a lot of food later as well, yeah? So this is in principle how you can compute this, and in an exercise we could do it. This is a quarter of an hour. We could develop all formulae which are necessary to compute such a strip. So if you would like to see how good your geometric computing is by now, this would be a good exercise. You are working on developables. It's a good exercise to write a little program which makes such strips. Yeah? Now, I give you a discrete version of this, because we also want to look at discrete things. And I look now at geodesic curves at shortest path, on an arbitrary surface. But for the moment, we do not take a surface, we take a polyhedron. So a surface formed by planar faces. Yeah? Then this polyhedron, at least locally, I can unfold. I take here two neighboring faces. They are here. I unfold. How do I get the shortest path on a polyhedron? I do an unfolding. And in the unfolding, a shortest path must be straight. The shortest connection between 2 points in the plane is a straight line. And since it is straight, you see, when we cross an edge, and this is the only interesting thing for us, how to cross an edge. Yeah? In the triangle or in the face itself, it will be straight. This is clear anyway. But how do we cross an edge? Under equal angles. This angle equals this angle. And this you see also here. How do we cross an edge? We have an incoming angle here, and this must be the outgoing angle there. So if you want to draw a shortest path on a polyhedral surface, you can start in a direction. In your face, you go straight. As soon as you hit an edge, you make this angle property, and you continue, and so on. There's one slight problem if you hit a vertex. This is a bit unlucky, but it can happen. And then one way is to say, at the vertex, I proceed so such the sum of angles on one side equals the sum of angles on the other side. This is one way how to do it at the vertex. Yeah? Wait a bit, yeah? Now we have on a smooth surface, shortest path. Yeah, shortest path. Has the property that at each point, again, the osculating plane, which we just had here, the osculating plane of the path is orthogonal to the tangent plane, contains the surface normal. Again, this implies that the geodesic curvature is 0, and this implies the shortest path property. But this you need to prove. So I'm not sure whether you are familiar with variational calculus of variations. This is a simple exercise for applying calculus of variations. Among all curves which connect 2 points, you look for the shortest one. And you will find out by something which corresponds to the derivative, the first variation. If you set the first variation to 0, what really comes out, geodesic curvature is 0. This is like if you are differential geometry, if you would like to compute the minimal surface, if you look for the surface which encloses a minimal surface area, given a certain curve, then you have to search among all surfaces. This is an infinite dimensional manifold. So you need calculus of variations. The calculus of variations, you have to set the so-called first variation, this is like the first derivative of a function, to 0. And the geometric meaning of the first variation equals 0 is exactly mean curvature equals 0. So this is how one can prove it mathematically. Now, and these geodesics are very interesting for applications because if we have a surface, now we have again our paper strip, we can take a strip of paper, a straight strip, and we can glue it on the surface, and it will always follow a geodesic. So you can say, for example, if you would like to panelize my surface with long, straight, say, strips of material, of bendable material, it will follow geodesics. Then I do not have the trouble of cutting so much off. And here are various examples of doing it. So this is from research at École Polytechnique in Lausanne, in Switzerland, where they have straight beams of wood, relatively thin, and they bend this wood and they come up with structures like this. And this forms a surface here. Natterer is an architect who has done such structures which are done basically by bending straight beams of wood, and they follow geodesics on the surface. And we have done some work which I'll show you later. Here? No, the middle curve is exactly here. This is the middle curve of the beam.
This is not unique? This curve is not unique?
No. Here I gave you a... Here I discussed how to find a shape which I get by taking a... I have my strip here. I did not even say I have it here. Yeah. So here is my strip of paper, what I can do with such a strip. Yeah, this is what I showed you. You will always have a middle curve. The middle curve is not shown, but how to get the surface is by taking this envelope of rectifying planes and doing the unfolding, of course, cutting it appropriately, and then, if you like, go back. Yeah? This is your exercise, which you will make. And then I have a surface, and I have many such possibilities to place a strip on a smooth surface. Do we have a surface here? No, it's too simple. Not the real surface. Oh, here, my chair. So this is a surface. And there is, of course, many ways of placing this strip here on the surface. And then, you have to... this is not so, because if you want to cover it densely by such strips, how to move forward here from one location to the other is already a research problem. We have worked on this previously, but today maybe I do not talk about it. And then finally, something which the students, Well, unfolding a general surface you cannot unfold. Yeah, but a developable surface you can cut and unfold.
No, maybe it's not.
A sphere, if I have a sphere, I can cut it. I have hemispheres or whatever, and it's not unfoldable. This is exactly this thing. I have a sphere. This is what my students always mix up. They do the following. They say, I have a sphere. Professor, a sphere is developable, and I prove you why. So you say, prove it to me. They go ahead, take a polyhedron which approximates a sphere. They come up with a discrete model of a sphere. And this I accept. And then they press the unfold button in their CAD system. And the unfold button will get this. And it is unfolded. So why is the sphere not developable? It is not developable because these triangles are not connected anymore. Look at this. You have everywhere these gaps coming in. So there is, even here, yes, there is no connection. There is no vertex where you have a full sequence of triangles around. And you see why you cannot have it. Because you will have this vertex star, as we call it, closed, if and only if the sum of angles is 2 pi, is 360 degrees. And having 360-degree angle around a vertex in such a discrete surface is equivalent to having vanishing Gaussian curvature. So this, but here, in this convex case, where we everywhere have positive Gaussian curvature, we have this nice fact, at least, this unfolding, also it is not really nice, but yeah, you can do it, not a smooth development. But it is connected. However, if you do the same for a negatively curved surface, your CAD system will give you something like this. Why? Because here, in such a vertex star, if you take a vertex and the faces around the vertex, let's say they are only triangles, yeah, and these angles, then the sum of angles will be greater than 2 pi. And in order to unfold it without overlap, you need to take at least one, maybe even more of these triangles out and place them somewhere else. And this makes this whole thing so terribly disconnected. And this is also something which appears in your project, right? This is exactly what appears in your project, this negatively curved. With these triangles and unfolding a triangle mesh is not the ideal method. You can, of course, you always have gaps, but you want to have the gaps along controlled, somehow nice curves when you unfold. Yeah. You want to have strips, so I would unfold them along principal curvature lines. Yeah. Anyway, this is a fact. Now, I did not yet tell you how to realize this on the computer, and here I show you some work done by a student of mine, by Cheng Tang, who told me that he has already sent you optimized meshes, so he's a good student. Cheng Tang, this is from his PhD defense. So you see what I expect from a PhD thesis. Yeah? But this is only a part of his PhD work. This is only maybe 1/4 of his work. So, developable surfaces. Yeah, this is not nicely seen here. This should be a sheep. But unfortunately, we do not see this sheep at all. If we close this, now the light is only coming here. This doesn't help. Yeah. You can see it. Yeah. These ship builders. So in ship buildings, they used also developable models somehow because they had these planar sheets or pieces of wood and then they put it on the ship, maybe with some gaps. There's also something which is very interesting, work by David Huffman. This is the inventor of the Huffman codes. Maybe you know this. I'm not in this area, but he's famous for the Huffman codes and actually not for his objects. His objects are also found from a flat sheet of paper by folding, but not folding along straight lines, but folding along curves. So you mark here curves, and then a kind curved origami. So this is what we call curved origami. You can hand it through it. This doesn't matter. Yeah, you can play. So such things, this was his task to do it on a computer. And let me see. Or something like work of Eric Demain, who is certainly known among everybody here because this is one of the big masters in computational geometry. He takes an annulus on a sheet of paper, creases along concentric rings, and then you shape it up. You will see it in a video later. Or then, of course, Geary. So, previous work on this direction. The mesh approach. We have discussed. Yeah, we said we can take these strips of planar quartz and by some nice subdivision approach combined with optimization for flatness, planarity of faces, we have an approach. It's also a mesh approach, and there is a spline approach, and which we will discuss in a little more detail here. And no, unfortunately, it's too short. Spline approach. There is one approach which I will discuss a little later, and then one which I came up with some years ago, where I thought, let us eliminate the nonlinear constraints. And to eliminate the nonlinear constraints, really the idea is extremely simple. I said the following: a developable surface is the envelope of a family of planes. Yeah? And how does the equation of a plane look like? The equation of a plane is, say, u0 plus u1 times, say, x1 is the first coordinate, plus u2 x2 plus u3 x3 equals 0. This is a plane. Of course, u0, u1, u2, and u3 are given. Yeah? And if this is a smooth family of planes, then this u0 depends on t, the u1 depends on t, and so does the u2 and the u3. I would like to write it in a more concise notation. I will write u0 of t plus, and then u1, u2, and u3 I collect into a vector u of t, so this is fat now, meaning a vector. And then this is, of course, the scalar product of two vectors, of the vector u with our running coordinate vector x, right? X equals 0. So this is a family of planes. Let's say capital U of t. Right. How do we compute? This is also something you should know. If we have a family of planes, how do we compute this straight line along which the plane touches the envelope? I told you, if I have a family of planes, it will envelope a developable surface, and each plane will be in contact along a straight line. How do I compute it? And the computation is extremely simple. I take the first derivative of this family, u dot.
Surface or curves? Tangent all of this surface.
No,
Planes.
all planes.
All planes.
Yeah, each plane is tangent along a straight line to the envelope. This is what we said before. And how do we get this straight line? We take the derivative, so u0 dot of t, plus u dot of t times x, this is an inner product, equals 0. So for a chosen t means a fixed position among my whole family of planes, a selected plane, a fixed t. I have here two linear equations, two planes. And I intersect these two planes. So the ruling equals the intersection of u of t with u dot of t. This you can do. And then in computer-aided design, one likes representations that are polynomial or piecewise polynomial. So then these u's would be spline functions or Bézier representation. And this is what we did. Maybe you know Bézier. Who does not know what the Bézier curve is? This is a better question. Yeah? You know. Okay. So then I write this u of t in a Bézier representation. Let's call this capital U equals u0, u1, u2, and u3. Yeah? All these coefficients depending on t, u of t. I can write in the form sum bni of t ui, polynomial. This I goes from 0 to n. Of course, the b n I of t is n choose I, t to the power of I, 1 minus t to the power of n minus I. This is Bézier. And now this looks like a representation of a Bézier curve, but in general, when you have a Bézier curve, you look for points. There, this would be a point. But here it is not a point, it is a vector in R4, it is the plane coordinates of a plane. So it is here a plane. So you have control planes, I do not go into the detail, and from these control planes you can compute the envelope. And now I think we have a video, because Cheng usually has very nice. Where is this video? Coming. No? Here. I do not know why. Really, this is very strange. I'm sorry. I was totally convinced that this will work here. But how do I get it? One moment. I'm sorry, but we really need this. I try. Why is it not working? So let me try another thing. Now it works. It is working now, so we finally got it to work. We have these control planes here, and the user manipulates the planes. And you see this envelope. Do you see these singularities coming about? So here it is nice. Now it is nice. And then you move this plane, it's still nice, but now you have here this singularity going back. So as an envelope, it is very difficult to control these singularities. All the time, these singularities enter your patch which you want to design. And therefore, this dual representation, also it is elegant because it removes all the constraints, does not remove the singularity. So it is not ideal. So what then my student did, he says, I want to have my surface as a standard Bezier surface. I explain it with Bezier, but we can do with spline as well. So you have here a Bezier curve, cubic Bezier curve, here a cubic Bezier curve. You connect, so this is the Bezier curve A of U. The next is the Bezier curve B of U. The connecting line is, of course, 1 minus VA plus VB. This is just a line connecting the curve point A of U with the curve point B of U. Now, what we need to ensure now is, let me probably draw it here as well, because this is really important. Otherwise, we will not get it. So here we have A of U. Here we have the point B of U. And this is this connecting line. And it is a correct connection. Before we discussed how to connect two curves by a developable surface. And you remember what I said. We must have a tangent here and a tangent here. Together with this connection, this must be one plane, which is the tangent plane. This means that the derivative vector here, A dot of U, the derivative vector here, B dot of U, and the vector B minus A have to be coplanar, have to lie in one plane. And now, instead of writing determinant of B minus A dot, and B dot equals 0. So one way would be this determinant B minus A dot, B dot equals 0. Instead of this, Cheng says I introduce an appropriate field of surface of normal vectors here, n of u, and I require that this n of u is normal to this plane. This means this n of u has to be normal to A dot, it has to be normal to B dot, it has to be normal to this direction vector A minus B or B minus A. And this is what he writes down. So this is this planarity condition. Now you need to think about the fact that if this is Bézier, A and B are polynomials, say of degree n. Then A dot is of degree n minus 1 and B dot is of degree n minus 1. So this determinant is of degree n plus n minus 1 plus n minus 1. This would be 3n minus 2. If you look a little closer, you see that the higher order coefficient goes away. So this is an of degree 3n, in fact, minus 3. And the polynomial of degree 3n minus 3 vanishes identically if it vanishes at 3n minus 2 points. Because then you have 3n minus 2 zeros, and it should only have 3n minus 3. So it's clear. This means that this is not infinitely many conditions. For each u a condition, I need just 3n minus 2 of these conditions. I could make my normals, I could take 3n minus 2 normal vectors as new variables, or I define these normal vectors in a Bézier form. So the message is, if we take Bézier, we just have a finite number of constraints, and the constraints are actually quadratic. Did you see? These inner products are 0. And now this is a system which my student has programmed up. This is this Bézier surface, do you see? And the user manipulates the surface. Let us run again. Sorry. So the user can drag the control points, but this is control point, yeah? But the other points also slightly change if you observe, because we have to maintain developability. If the user would just drag around the control points, you would have very nice ruled surfaces, but they would not be developable. And this is a system which automatically finds the nearest developable surface. So the user changes the control points and, yeah?
The control point appears in this formula.
Here?
This control point.
Yeah. A of, yeah.
This equation.
A of u equals, I did not write it down, has the form sum of Bni of u now, sum ai, I from 0 to n, and these coefficients here are the control points. So in my figure before, this was n equals 3. So you have control points a0, a1, a2, and a3. Right? A cubic polynomial has 4 coefficients here. And in the Bernstein form, and likewise with the b. So these are the control points. But as you see, you cannot fix all points and manipulate just one, because then you will for sure destroy the developability. Now, the thing is more complicated, because if you would really like to model developable surfaces, you will not work with one Bézier patch. I mean, this is nothing. You need B-splines, and you need these nasty connections of planes with smooth patches. This will pop up in practice. So if you take a sheet of paper and you fold it up, in most cases, first of all, you get some creases if you are not careful. And it is also quite likely that it is not just one tangent surface, but is a composition of more developable surfaces, of several patches. So we need to care about such patch combinations, combined patches. I would say this is software engineering to do it right. This is a little bit of work, but this is not theoretically difficult, this multi-patch stuff. And here you see, no, it works. His system, so interactively, but this is not This is programmed by himself. This is a C++ program. It's not from some CAD system. And he has certain manipulation techniques. And this whole thing here, what he manipulates, is only composed of developable patches. So you could make a model, and then you could manufacture it from steel, for example, or aluminum, and bend it up. Yeah? Yeah, exactly. No, yeah, of course, yeah. Exactly, yeah. Exactly. Now, he can do more, but here I do not show you the details. This is a lot of work. This is such a strip of paper as we have just seen before in the theory. And here now it changes the orientation here, turns it around, and generates a Möbius strip. So you know Möbius strip, you take it, turn it around once, and you get such a thing which doesn't have one side. So if you start here on one side and you go around, you move on the other side, and so on. Yeah? So this is a one-sided surface, a Möbius strip. What you also should observe, maybe I run it again, because it is important to realize that during isometric deformation of a developable surface, these rulings, the straight lines on the surface, will change. So the ruling preserving deformations are too restricted. So you will see they change during the optimization, the orientation of these rulings. And this makes the whole thing a little harder to implement. Now I come to this curved folding. Curved folding, folding a piece of paper along a curve. How can we do this mathematically? And the trick is again lying in this geodesic curvature which we have discussed here. I said during an isometric deformation, the geodesic curvature does not change. So if we have such a curved fold here, so here we have such a crease curve, and if we unfold this into the plane without cutting it, yeah, and unfolding it separately, if it keeps together, then the geodesic curvature of this crease curve with respect to this developable surface and with respect to the other one has to be the same. Otherwise, there is no way that this keeps together. Yeah? The condition that this geodesic curvature for this and this strip equals, you can easily translate into the fact that the osculating plane of your crease curve forms the same angle with the tangent plane on either side. This is clear, yeah, because the inclination of this curvature vector determines the geodesic curvature. And so you do the following. If you have one surface here, you get the other one by just taking from this crease curve the osculating planes and then mirroring the tangent planes here, reflecting to the other side. This is just reflection. And then they envelope the second side. Or in this constraint system, you have to write the constraint, and this is written here, that the normal on the left side and the normal on the right side have the difference. Yeah? The difference has a vanishing inner product with the second derivative. This is exactly the same. And this is a nice bilinear condition again, and this can be exploited. And now let us see what Cheng Cheng has done with it. Isometric deformation, this is now his program, where he can isometric deform this shape, and it always, you see here you form a cylinder on this side, and the other thing is determined. So you, by the way, this shape has an application. It appears in certain packaging machines. Yeah, so it has even this shape has an application. Okay. Now then, if you fold something like this, individually you have a lot of creases where you have to apply this property on the osculating plane, which I said just before. But here the vertex, if you would like here, if you like to fold it down, then of course here the sum of angles has to be 2 pi. And this has also to enter as a constraint. And then you can also do such vertices. Or, this is another more elaborate example. This is a little bit the history of the making, and this is the final result. And then he made a paper model out of it and could confirm that it looks very much like the designed model he had on the computer. And now this Eric Demain object, you take, let us go back one moment. So you start with an annulus, and then you start folding along concentric rings. This is accelerated, so the program is not as good that it would be as fast as this. This is accelerated by a factor 5 or 6, it was shown. This is an isometric deformation, and it includes all these constraints for being a curved fold. And this is then already a pretty large system. And at least on the machine he is using, which is certainly a nice PC, but not GPU accelerated here. So this is just normal CPU.
How do you define this deformation?
Now this is interactively. He can manipulate these points and then have a certain bending energy, which is also minimized. No, this is not a big deal. Why am I back? Very strange. This is the result now. So this is the flat state. Here the rulings from this in the isometric deformation, and here's the folded state. And maybe, what one can also do.
I don't know. Excuse me.
Yeah.
You define this deformation. You define this isometric deformation, or there is a canonical.
No. This is interactive modeling. You drag a few points, and then you have some energy which you minimize to make it more unique, right? This is not an explicit formula. So there is no. Unfortunately, in fact, it is an unsolved. Since you like unsolved problems, it is an unsolved problem whether this domain ring here. So Eric Demain doesn't know, which says quite a bit. This domain ring, whether it exists in a mathematically precise sense, whether you can really find such a family of smooth developable surface strips where this curved folding condition is satisfied precisely everywhere, so that the development are concentric circular rings. If you go away from concentric, sure it exists. Yeah? To do something like this is clear. But concentric circle is not clear because of this closing condition. So this is not obvious at all. So I think one must come up here with some very specific type of curves to start with, something like constant torsion or something like this. Yeah? Curvature, of course, because this is, curvature, constant curvature curves you need to do. Maybe this just without much detail, because maybe I show you how to do this approximation. Maybe we could do tomorrow, but since we have this presentation. Again, decomposition into strips. I show it to you guys who do this project. Of course, this is not an architectural model, but in computer graphics, the people really like this so-called Stanford bunny. And one can come up with a system that does the following. The user marks certain regions, and the system immediately computes an approximation. You see how fast this is? An approximation with a developable surface patch. And then the user can somehow make sure that these patches connect up nicely. This is an interactive design, some global optimization, and then this is the result. This is the bunny in a stripified version, or here you have it made from some metal. Yeah. It looks quite nice, yeah. It looks nice. So And I think this is what, yes, this we do not look at. So we have now done with these developable surfaces. And here I let you choose. So I have now 45 minutes, 40 minutes or so left. Is this true? No. 10 minutes left. Yeah, this is 10 minutes. And in these 10 minutes, we can either go into support structures, which is a little bit tough maybe. Then we can go into what we call, you had circle packings yesterday, right? So let's go into the circle packing stuff. Circle packing. So we call this circle packing meshes. This is more discrete stuff, so it will be liked by computational geometers, hopefully. Now, we were inspired by a building in Birmingham that looks like this. It is arguable whether it is beautiful or not, but I don't care. It is a nice mathematical structure, and it is a kind of circle packing on the surface of this double curved architectural skin. And now we wanted to design such. This was actually a master's thesis which I gave to one of my students in Vienna. And so he started from planar circle packings. Circle packing in the plane, the figure says what we mean. We mean triangular combinatorics, so we have always these three circles with pairwise tangency. Yeah, this is a circle packing with triangular combinatorics when we connect the centers of circles which are in contact, we get a triangle mesh. Such things we consider. We do not consider this. This is a very nice structure also. This has quadrilateral combinatorics and is in fact slightly more appropriate for surfaces, but it has been investigated already by the group of Alexander Bobenko in Berlin. So these circle packings are related to isothermic surfaces. This is the differential geometric thing. But we take the triangular combinatorics. Now the question arises, can we do it in 3D? In the plane, obviously we can do it, but can we do it in 3D? Now let's look at three circles which are pairwise in contact. If two circles are in contact, this circle is tangent to this circle, then 3D configuration, not in one plane, then the rotational axis of this circle and the rotational axis of the other circle must intersect. This is just by symmetry with respect to this middle plane. This is obvious. Yeah? And then if we have another connection, another circle touching these two, it again must intersect. So we have three axes which pairwise intersect. There would also be the case that these three axes lie in a plane, but this you can rule out. You cannot go around that. It gives a structure which is undesirable here. So the only way that three circles are pairwise tangent is that their axes intersect. But if their axes intersect, what does this mean? You know, a point on a circle, on this circle, all points on this circle would have the same distance to this point because the point lies on the rotational axis. All points of this circle would have the same distance to this point because of this contact point. So in fact, all these blue points here on these circles would have equal distance to this point. This would be everything lies on a sphere. And this, of course, we knew from before, because if I can do it in the plane, I can apply a so-called inversion, and I can map it to the sphere. So this is clear. It exists on the sphere, but it exists only in the sphere and on the plane. So this is not generalizable to 3D. So what can we generalize? This is the question. We generalize this thing. If we have a circle packing of these red circles, then it turns out that if you pick here a triangle in this associated triangulation, and you take the in circle, this in circle must be contacting with these edges here exactly at the contact point of these two circles. This is obvious because if you have three circles which are tangent, you take here this tangent, and this tangent. They intersect at the point which is at equal distance to these three circles, and this is the in-center. So this is obvious. So associated with a planar circle packing is a so-called triangulation with an in-circle packing. So in this triangle we have inscribed circles. This you always have, but here we have the property that if we take two triangles, neighboring triangles, we take the in-circle here and the in-circle here, we have the same contact point. This is the definition of a circle packing mesh. And this you can do, circle packing mesh, if the in-circles form a packing in this sense. So same contact point along shared edges. This is generalizable to 3D. This is already a 3D version. Obviously, if in 3D we take a vertex of this triangulation, and we take this in-circle here, then this length here is the tangential distance of this point to this circle. It is the same as this tangential distance, because if we have a circle, the tangential distances from a point is the same, and we can go around everywhere the same tangential distance. I can take a sphere with this center, passing through all these contact points, and I can do this also here. I also have a sphere, right? I have a sphere here, and two adjacent spheres meet at this point in contact. So we have associated with a in-circle packing, we have a precise sphere packing in space. So somehow the circle packing generalizes here to a sphere packing. And the circles are just this in-circle packing. And then we set up an optimization, which I do not show you in detail, but it is very, very simple. Just you introduce these spheres and the radii of these spheres. So the midpoints of the spheres, the centers, are the vertices of our triangulation. It's simple anyway. And the radii you introduce as variables. Your initial triangulation is not circle packing. Here it is very easy to see, right? You have two adjacent triangles, in circle, but the contact points are very far away. They should be the same for an in-circle packing. So like here, the same. And this optimization will make it. The question is, yeah? Triangle mesh. Yes. And, yeah, very good question. Triangle mesh is important, yeah? And the triangle mesh gives you a certain shape, and we would like to stay close to this shape. Right? So, at least the boundary we would like to keep. But as close as possible to the shape. This, yeah, maybe I should also say this. Circle packings in the plane are related to something which you have addressed today, which are conformal maps. So, a conformal map in the plane is a map which preserves angles. It does not preserve lengths. It preserves intersection angles. And a discrete version of representing conformal maps is to start with a circle packing and to transform it into another circle packing. Right? This is a discrete map. This is very well known. There's a nice book by Ken Stevenson about these circle packings. Now, we have here a kind of 3D version of it, and we are bound by a fact from differential geometry, conformal geometry, namely that there are different equivalence classes of surfaces with respect to these conformal maps. So there is this famous theorem which says if you have a a surface which is of disk topology. This means simply connected. Yeah? Disk topology. Topological disk. I have a surface here and a surface there. Both are topological disks. Since there exists, it's not unique, but there always exists a conformal map which maps one to the other. So the set of conformal disks is one of the conformal equivalence classes. Likewise, if you have a surface of sphere topology, so like the sphere or any other simply surface of the same genus as the sphere, closed surface, then we can map them conformally onto each other. This is no longer true, for example, for a torus. If you take a topological torus and a second topological torus, in general, they will be of different conformal equivalence classes. And since there is no conformal mapping from this one torus to the other torus. And we are here exactly facing the same problem. If we do this optimization for topological disks or spheres, we always succeed with any initialization. And if we do it with other surfaces, in general, we will not succeed. So the initialization is a bit hard, but I show you results. So this is an open, let us take it. Yeah? A circuit packing for a smooth surface. But definitely not by Euclidean surface, for sure not. There is no circuit on a smooth surface in general. You could try geodesic circuits. This is possible. Yeah.
Is our initial triangulation arbitrary?
Yes.
There is no surface.
Yes, there is a reference surface. Yeah. There is a reference surface. So I give an example. You have a dome-like shape. You have a boundary. This is a topological disk, such a dome. You start with a triangulation. And then you optimize. You have to make sure that the vertices on the boundary are allowed to glide on the boundary. This I discuss tomorrow, because for implementing things, this is extremely important. And that the other vertices are allowed to glide on your surface, or close to your surface, and then the optimization will succeed. Yeah. Yeah, this we do not need. Yeah. You can come up with various derived structures, which I think the time is over. You can, for example, not make a circle packing, a precise one, but you could come up with a tiling of a surface by planar hexagonal tiles and triangles. So this is something which you can derive from the circle packing. You can almost see it. And what you can also see, you can do something like this. This looks like a circle packing of a smooth surface, but there is some imprecision. It's not the precise circle packing, because we have proof it doesn't exist. But these circle packing meshes allow us to come up with ideas to do it approximately, and you can. This is a paper which we published in 2009 at SIGGRAPH Asia, so you would be able to see it there, and I can also give you a reference. But since the time is over, unless there may be questions. So this last topic, I realized this was a little bit of a rush, but I wanted to show you that certain things do not exist. And yesterday you had this software with the circle packings. Was it a grasshopper or kangaroo? Kangaroo. I know this guy, this Daniel Piker, and this kangaroo guy, he implemented actually this method, exactly our paper. It's very easy to implement. Yeah? So he implemented exactly the circle packing measure. So in kangaroo, this is actually turns out to be a very easy optimization. It's much easier than doing planar quads. So it converges very nicely, of course, in the same conformal equivalence class. So I'm done. Thank you. Let us close.